Hey everyone, I'm David Kassan. I'm a software engineer at SUSE, and I'm here today to talk to you about the Elemental project, and more specific to talk to you about the Elemental Toolkit, which is one of its components. The title of this presentation states, Build Your Own K3s ready OS like a pro. And in this presentation, we're going to look at how to make use of the Elemental Toolkit to build an opinionated and cloud-native Linux OS image. This presentation is divided into different 5 sections. On the very first one, we're going to look at what is the Elemental project, a quick overview of the project and its components. Then we're going to look at the Elemental Toolkit, which is the central piece of this presentation. Following that, we're going to see the anatomy of an Elemental OS, which is basically the outcome of using the Elemental Toolkit. On the fourth section, we're going to build an Elemental OS. We're going to follow an example of building an Elemental OS based on OpenSUSE distribution. And finally, on the fifth section, we're going to talk about the Elemental teal. The Elemental teal is essentially the specific appliance, the specific Linux image we are providing within the Elemental project that's been built with the Elemental Toolkit. So what is the Elemental project? Generally, we like to say that the Elemental is a software stack designed to enable OS management within Kubernetes. Hence, it provides a centralized and cloud-native OS management solution, and it is based on standard and generic tools to bring Rancher and SUSE to the edge. I like to reinforce here that it is based on standard and generic tools. We are not reinventing the wheel, we are just using widely adopted and established utilities and Linux projects. We're just providing a procedure on how to build a Linux OS and how to manage it within Kubernetes. Moreover, since we are a Rancher project, Elemental is provided as a Rancher Manager extension. Note this presentation is not targeting Elemental as a whole. So for a wider view and a tutorial on Elemental as an edge solution, please don't miss Mastering Edge Ops talk given from my colleagues Michele and Luca. So let's have a look on the Elemental project components. Elemental project can be mostly divided in 2 different areas. There is the Elemental operator, which is the Kubernetes operator that brings OS management to Rancher. This is the responsible to attend node registration, node bootstrap. It's also responsible to kickstart Rancher provisioning plans, and it also orchestrates node upgrades from OCI artifacts. So basically, this is all Kubernetes logic. All the Kubernetes logic is part of the Elemental operator, which is in turn a Kubernetes controller. Then on the other side, there is the Elemental Toolkit. The Elemental Toolkit is the set of utilities to build and run an Elemental OS image. And Elemental OS images are the OS images that are meant to be managed by the Elemental operator. So at the end of the day, an Elemental OS image is nothing else than a generic Linux image with a thin layer of software on top of it. So now I would like to make a point on what is and what is not the Elemental toolkits and Elemental OSs. So basically, an Elemental OS is not a Linux distribution. I want to make this clear. We are not providing a new Linux distribution. We are just basically crafting an OS image based on top of a given Linux distribution. We are just providing a way and an opinionated way to build an OS image, not a distribution. Also, an Elemental OS is not a general purpose OS. It is designed, tested, and verified with the sole purpose of running Kubernetes. Moreover, Elemental Toolkit is not coupled to Kubernetes, neither to any specific Linux distribution. In Elemental, we try to keep things simple, so the Elemental Toolkit is just the utilities to build a Linux OS. Nothing to do with Kubernetes, and is not tied to any specific Linux distribution because it just makes use of well and widely adopted Linux utilities, which are commonly available to any distribution out there. In addition, Elemental Toolkit is basically used to build the Elemental teal, And as I said before, the Elemental Teal is our custom appliance that meets together the SUSE Linux Enterprise micro distribution together with the Rancher Kubernetes, which is K3s and RKE2. So Elemental Teal is based on SUSE Linux Enterprise distribution, and it takes advantage of it. It just takes the maintenance updates and the security updates from it. We are just not providing from Elemental team our own security updates for the OS. We just rely on the given distribution. In this case, SUSE Linux Enterprise Micro, a rock solid distribution. So now I'd like to give a view overview of the Elemental Toolkit principle. The Elemental Toolkit aims to provide the tools and the configurations to manage Linux OS following cloud native principles. And the very first thing we'd like to note is that an Elemental OS is built and delivered as a simple OCA container. It is built and delivered as a simple Docker container to some extent. So basically, that means that there is a container containing the kernel, the init ramfs, the drivers, and everything that an OS needs. So we all know that the containers are bread and butter for Kubernetes. Hence, delivering the OS as a container from OCI registries, it makes easy to interoperate, to integrate into Kubernetes ecosystem. Moreover, if we want to make use of the underlying OS as if they were containers, we want it to be immutable. So the Elemental Toolkit is also responsible to provide an immutability layer for the OS. And in addition, we also want to follow the cloud-init style configuration. So Elemental OS is configured with cloud-init style configuration. Basically, that means we are compatible to some extent to the essential cloud init or cloud config files, despite we are not using exactly the cloud init project. More on that later. Then another aspect that is relevant for Elemental Toolkit is that the, the outcoming OS needs to be upgradable from Kubernetes. So it has to be pluggable to projects like System Upgrade Controllers. For those who are not aware, a System Upgrade Controller is a Rancher project that allows to run a privileged pod in nodes that are capable to modify the underlying host. So, from an elemental point of view, we are using a System Upgrade Controller to run the Elemental OS as a container, as a pod, to actually dump itself to the underlying disk. And finally, last but not least, it might be obvious, but we are following DevOps practices in our Elemental project. We develop, build, and deliver following DevOps. So we embrace automation from the very beginning, from GitHub pull requests up to staging builds in the open build service. That's relevant because it allows us to set strong continuous integration, strong testing, and this allows us to quickly provide fixes in case of bugs, and it also allows us to quickly update the build in case of maintenance update or security fixes coming from the underlying distribution. So, what is actually the Elemental Toolkit? How it is built and delivered? So, Elemental Toolkit is built and delivered as a single Golang binary. We tend to call it the Elemental client. So it's an easy to distribute and deploy binary. We just have to copy to the desired place. So this binary provides a set of commands. It provides the install command, which is meant to be used as an installer. It can be used to install an Elemental OS container to a disk. There is the upgrade command, which is used obviously to upgrade an already running Elemental OS to another version. And we also have the reset and the build ISO, etc. These commands are all using standard tools for formatting, partitioning, copying data, etc. We just rely on common and widely adopted Linux utilities. So no rocket science here, not reinventing the wheel here. In addition, this binary also provides a set of embedded OS configurations. So these embedded OS configurations include the bootloader configuration files. So it also includes the grep configuration files. In addition, it also includes dracat module files, and this dracat module is the responsible to set the immutability of the OS. So this, in order to set the immutable or the immutability feature in an elemental OS, is enough just by dropping in it the dracat module files. And in the other embedded OS configuration files, we are also including in the binary are the systemd services to define and to set the cloud-init boot stages. So the stages where we can actually run certain configuration files. And in addition, it also includes default and very basic cloud config configurations, like the ones needed to set a root user and similar stuff. What I like to outline from this slide is that there are three Linux projects marked in bold. More specific, here we have marked in bold the bootloader, the grep. We have marked in bold dracat and also systemd. These are the assumptions that the Elemental Toolkit is making for the underlying Linux OS. So this is where we are coupled. We are coupled to grep, to dracat, and systemd mostly. So any Linux distribution that makes use of grep, dracat, and systemd is a candidate to be used within the Elemental Toolkit. Again, Elemental Toolkit relies on widely adopted and tested Linux technologies. So now we are going to have a look on an Elemental OS itself. How an Elemental OS looks like once installed into a disk. So here we have a diagram of the partition table of an installed system, and it is basically divided into 5 different partitions. The first partition is the EFI partition, which is just for bootloader artifacts, pretty obvious. Then there is the OEM partition. The OEM partition is a tiny partition that we use to store custom cloud configuration files. Nothing else than that, so it's just a tiny partition, and it's usually mounted with read-write permissions and persistent. Then there is the recovery partition. The name already states and defines its purpose. It's meant for recovery procedures. It basically stores the recovery image, and the recovery image is nothing else than a file system image containing the whole root tree of an Elemental OS container. So during the installation of an Elemental OS container, its root tree is dumped into a file system image and stored as a file in the recovery partition. Then there is the state partition. The state partition includes the active image, and after a clean install, active image and recovery image are essentially the same. The active image is the image that aims to be booted at on a regular basis. So the active image is a file system image including the Elemental OS container root tree. And then there is the fallback image, which again, the name already suggests what it's meant for. So the fallback image is used to just fall back to a known state. So in case we upgrade the active image, we are going to copy before upgrading it into the fallback, so we can keep the previous known stage in a known location and just upgrade the active image with the new contents. So in case there is something going wrong, and if the boot fails on active image, we're just going to reboot on fallback, which is going to be the old pre-upgrade OS system. So it's just to allow a rollback in case there is an upgrade issue. Moreover, in the state partition, we're also including some state metadata, which is just storing some installation metadata information, like the labels of each partition and the labels of each file system image. And we are also including in the state partition the bootloader configuration. The bootloader configuration stays static across updates and never change. It's not expected to change during the life cycle of the system. Finally, there is the persistent partition. The persistent partition is simple. It's just the partition it is meant to be used for storing data. It is mounted under dash slash user slash local and is mounted with read write permissions. And there is where we are going to store all the persistent data we need to keep across reboots. So, as we said before, the elemental OS also needs to be immutable, or it aims to be immutable. So, to keeping with the elemental principles, we like to keep it configurable and simple. So, the mutability on an elemental OS is defined by basically mounting the OS root tree from a file system image that's mounted as a read-only loop device, so it cannot be changed. Of course, to make the system functional, there are some paths that need to be read-write and that require modifications during runtime. So, in within the elemental OS immutability approach, it is configurable which paths are read-write, and it also we can divide them between ephemeral and persistent paths. So the ephemeral paths are the ones that are basically configured as an overlay FS layer on top of a tempfs file system, so on memory. So all the changes are happening in memory, and the persistent paths can be configured as an overlay layer on top of the read-only file system based over the persistent partition. So the changes are going to be kept and are going to persist across reboots. Sorry. In addition, the persistent configurable paths can be set to be overlay FS layers, and it can be set to be bind modes. Given that most of the persistent paths are just going to be empty on the clean install, using a simple bind mode is just enough. So all this configuration happens dynamically in initramfs on early boot stages. So that means that the mutable layout is not set in stone. It's just configured at boot, and it can be configured from a cloud config file. So it can be highly customized to meet or to match specific use cases. So now let's have a look at a specific configuration of the mutable layout. And here is the cloud config file that actually configures it. And this is basically just defining an environment variables file. So this is just defining environment variables in a file, and this is just gets read at boot on early stages, and from that the drag-out module computes an fstep file, and from there on the fstep file is cornered by systemd. As simple as that. So there is no big magic within this drag-out module of Elemental. So just give a quick look on what is configured here. Actually, we can actually configure the overlay size, the in-memory file system size. So in this case, it's configured to be or to match or to make use of 25% of the available memory of the system. So we can configure the size of it. And we also configure which paths are going to be read-write. These read-write paths are the paths that are going to be ephemeral. So in this case, the only paths that are ephemeral are var, etc, and serve. Then we define the persistent volumes, and we can have multiple persistent volumes, but usually just one is the way to go. And basically, we just define the label of the file system of the persistent partition and the mode point. So we just set the label to cost persistent, and I include the mount point on it, and that's going to be honored. Finally, we just include the list of the persistent paths. In this case, as probably you can see, the persistent paths are mostly devoted to Kubernetes and Rineshare specific paths. So basically, these are mostly devoted to keep and to persist the K3s or RK2 installation across reboots. So let's jump to another fundamental aspect of an elemental OS, which is the cloud-init style configuration. I think I already said it before, but we are not actually using the cloud-init project per se. We are using an alternative Golang implementation based on Yip. Yip is an upstream project. Here is the link. And the main difference between cloud-init and Yip is that Yip configurations can be applied on different stages. And in a Yip system, the stages are just a label to define a set of configurations. So they can labels can be anything, stages can be anything. And within the Elemental project, we just predefined a few stages to be honored and executed at boot. So there are some systemd services that execute certain stages at boot. We have, for instance, the init stage that is actually executing cloud config files before switching to the real root, just inside the init There is the network stage, which is actually executing configurations once network is online, etc. And in addition to that, we have also defined another kind of stages in Elemental. We tend to call them hook stages, which are meant to customize certain maintenance procedures like installation and upgrade actions. So, for instance, we have before install and after install stages that can be used as hooks to modify the install procedure. The same applies for the upgrade and reset and other maintenance procedures that are commonly used in Elemental. So basically, Yip has its own syntax, but it also supports a subset of Cloud Init syntax. So there is an essential subset of a Cloud Init syntax that is supported within Yip. So it's likely that any cloud config file you have out there is already supported and capable and possibly to be used within Elemental without even changing it. So continuing on the Elemental OS cloud-init style configuration, I'd like to basically briefly discuss how we would configure an Elemental OS following the approach of day 0, day 1, and day 2 concepts. So for instance, how we would configure an Elemental OS in day 0, the development phase. So as we already mentioned, the Elemental OS is just an OCI image. So we can easily make a derived image out of an Elemental OS container. So we can simply just create a Docker file that is starting from an Elemental OS container, and in that Docker file just preload cloud-init files or add or remove some specific software. Then in day one, in the deployment phase, we could eventually include additional cloud-init files in several ways. We could include cloud config files as installation artifacts, so meaning that we can tell the installer to include additional extra files into the installation, into the installed system. Or we could eventually use another approach, which is basically using the hook stages we mentioned before. So we could actually include before and after installation hooks just to modify the installation behavior. For instance, we could use an after installation hook just to include additional software into the Elemental OS container or into the Elemental OS image. So basically, the Elemental OS container is dumped into a file system image, and the after installation hook has the capability or the potential to modify this file system image. Finally, how we would configure the Elemental OS on day two, on post-deployment phases. So additional cloud config files can be included within the OEM readable partition at any time. So there is this OEM partition in an Elemental deployment that is meant to keep custom cloud-init files. So we could just eventually include files in there, reboot, and they are going to be parsed and executed and honored. However, if rebooting is not an option, the Elemental client allows to run any stage, any cloud init stage at any time. So, for instance, if we want to include a cloud init stage to configure the network and we don't want to reboot it, we can just simply include the file into the OEM partition, execute the network stage, and that's going to apply the configuration. And in any follow-up reboot, this is going to be applied to. Finally, Elemental follows the principles of the immutable infrastructure. So post-deployment changes are meant to be minimal. So we expect that nodes can be recreated at any time. And we also, within the Elemental client, provide the reset command. The reset command allows us to reset the system from the recovery partition. And in that reset process, we can decide to keep or not to keep the cloud init configuration files. We can decide to keep or not to keep the persistent data. And we can also customize this reset procedure as as with reset hooks, the same way we would do with the install or the upgrade hooks. So we have chances just to alter and modify and customize the Elemental OS in day two. So following on the next section, we're going to build an Elemental OS, and we're going to see how it can be built from a generic base image. A generic base image, I understand it as a generic container image from any distribution. For instance, what we would get if we actually do a Docker pull OpenSUSE leap, we're going to get a container that per se is not doing anything special, but it's just meant to be used as a base image to just create another workload. So, for instance, in this case, this is the recipe here that is needed to create an Elemental OS. So it's divided in 5 steps, and it starts basically by installing the OS essentials to the base image. So if we are pulling a base image, a base container image, we need and we want to build an Elemental OS, we should actually make a Docker file that starts by installing the OS essentials to the base image, which are these OS essentials. So the kernel, systemd, dracat, grub, parted, etc. All the tools that we need in an OS that are usually not part of a container. Then on the second step, we need to install the Elemental client. The Elemental client, it is the binary coming from the Elemental Toolkit repository. We need to include that Golang binary. Then after that, we need to run the Elemental init command. The Elemental init command is the responsible of adding into the system the embedded configuration files. It is going to install the bootloader, dracat, and cloud init configuration files. Note this is only installing cloud configuration. It's only installing configuration files. It's not running any specific logic. Just drops some config files to the system. After that, we would have to rebuild the init ramfs, the initRD, basically because Elemental init includes a new dracat module. The init ramfs needs to be rebuilt, and this is going to be needed to get the Elemental OS to be mutable. And finally, the last step is just running some final touches and refinements according to the use case. For instance, installing additional software, adding some metadata, some specific configuration that is needed in for the specific underlying Linux distribution or use case, etc. So we're going to have a look now to a Docker file that actually follows these 5 steps. So this is a real functional example. This is an example that is building an elemental OS based on OpenSUSE lib 15.4. So obviously from the very beginning, we just set the underlying base image. In this case is the OpenSUSE lib 15.4. And after that, we just start with 5 steps we mentioned before. So in the very beginning, we start installing all the essential packages. Which are those packages? So basically kernel, systemd, grub2. You can see there is quite a long list of packages, but none of those is something strange or specific. So it's very essential teams, very basic and essential tools. So network manager, there is rsync, there is targ, zip, etc. Once this is installed, then we can follow up on installing the elemental client. So to install the elemental client, as we already said, this is just a Golang binary. So we just need to get it from the release URL, download it, and put it inside the dash user dash bin so it can be found within the path. Once the elemental client is installed, we just need to run the elemental init command in order to get all the configuration files into the system. So the configuration files for the bootloader, the configuration files for systemd, and the configuration files for Dracat. After that, we have to recreate the init ramfs, so we have to call Dracat to generate again the init.d. So this way, we include in it the new added Dracat module, the elemental module for the immutable feature. And after that, the only thing that's remaining is just some fine tuning and some customization according to the specific needs of the system. So in this case, we need to enable the essential services like Network Manager, since we're using Network Manager and Network Manager is not enabled by default on OpenSUSE lib. We need to enable it here. So system cattle enable Network Manager service, and we also want to have the temp, the dash temp, slash temp path to be ephemeral and to be on top of tempfs. This is already common in many distributions. So we just add and include the expected mount systemd unit. And after that, we just include some metadata within the system. So we just expand the OS, the etc OS release file to include some metadata that can be used later in time to identify where the system is coming from. And finally, last but not least, in this container image, we also add a command. This is just good for validation. As we all said before, the elemental OS container is a regular container, so once the build is done, it's nice to be capable to actually run docker run my new build image and being dropped in a shell. So we just include a command to a bash shell. So once we run this Docker file, and the build is going to last just a few minutes because it's mostly only installing additional packages on top of the base image. There is no difficult procedure in here, let's say. There is no complex procedure. It's a matter of installing additional packages mostly. So the build can be done in a few minutes. And once the build is done, the only thing that's left is just pushing it into the registry. So as mentioned before, this is a regular container image. So we can push it to an OCI registry. So we could eventually docker push, and the image is just up in the registry. So once the image is in the registry, what's next? What we do? How can we use it? So we could actually convert it into a bootable media. Nowadays, that means creating an ISO. So we could call elemental build ISO and refer to the just pushed container image. And what it would actually do is actually download the container image, extract the root tree, and build an ISO out of it. This ISO is going to be bootable, and this can be used to actually install Elemental into a bare metal system. In addition, also we can actually use this image in the registry to install it to a disk. So we can call Elemental install, refer to the image in the registry, and include the target disk, and then the magic is going to happen. Then Elemental install is going to partition the disk, set the partitions as we saw before, and just create the file system images containing the root tree and everything. Finally, also we can use the image we just pushed to a registry to directly upgrade from an already existing elemental system. So if we have an elemental system somewhere already running, we could simply just run elemental upgrade and include the URI of the just created image, and this is going to upgrade to that. It's just going to again just download the image from the registry, create a file system image with its own root tree, and just swap it from active to fallback, and we are done. Reboot, and we are just in the new upgraded system. So the thing here is that the OS is treated like a full stateless blob. So the whole OS is just a full stateless blob. So we just take it as a single artifact. So no RPM, no package manager involved in upgrades. And also the elemental OS is delivered from a container registry. So it is Kubernetes friendly. Kubernetes already understands registry easily, so it can be easily integrated into a Kubernetes ecosystem. So finally, we're reaching at the end of this presentation. Let me give a quick talk about the elemental teal. So elemental teal is where the green from Slim Micro meets the blue from Rancher. So teal is basically referring to the mixture of green color with blue color. That's where the name comes from. Pretty obvious. So basically, Elemental Teal is an OS based on Slimicro for Rancher container image. The Slimicro for Rancher image is a containerized and stripped to the bones operative system layer. It is a base image that already includes all the packages we had listed in the previous Docker file. At the very beginning of the previous Docker file, we were installing a bunch of packages, including the kernel, including systemd, etc. And a Slimicro for Rancher container image already contains all these. And its sole purpose is to actually run Kubernetes, K3s or RK2, and upgrades and maintenance duties are just controlled through Rancher Manager via the elemental operator. That's the whole story. So basically, the elemental teal, it's the same as we saw before, with few additional software actually to talk and to connect with the elemental operator. That basically means that the elemental teal, in addition, includes the Rancher system agent and the elemental register commands to actually connect with the elemental operator first, and then to actually follow the Rancher provisioning later. So Elemental Teal is fully supported on x86 architectures, and we also provide experimental ARM builds. ARM builds are called to be experimental because they are for now only tested on Raspberry Pi for Model B. So since they are only tested on Raspberry Pi, and currently it's hard to actually get Raspberry Pi nowadays, this is considered experimental for the time being. As soon as we get some, let's say, business demand on some specific ARM board, then we're going to dive into it and to provide whatever is needed. So we are not doing anything ARC specific in Elemental, hence there is no reason just to exclude ARM architecture from Elemental Project. So finally, we're leading to the very end. Something I like to reinforce is that Elemental Teal is enterprise ready. And what means it is enterprise ready? It means that we rely on well-established SUSE Linux enterprise procedures to evolve, build, and release OS images. Basically, it means that we are following well-established SUSE procedures within the Open Build service to build and release our artifacts. So we embrace automation to get stuff included quickly within the Open Build service. And Open Build service also providing us with reproducible builds with SUSE assigned artifacts. And it also means it's easy to rebuild and to release based on the underlying code stream updates. This is relevant. So if we get from SUSE Linux Enterprise security updates, we can quickly rebuild. Actually, it gets rebuilt automatically, and we can quickly test and verify there are no regressions and just release it. So it allows us to react in a quick and safe way. So that's basically all of it. That's all I had to explain for you today. Thank you very much. I hope you enjoyed it.